Hi everyone, welcome back. The learning goal for this video is to be able to use electronegativity to determine the polarity of a bond. And the electronegativity values are shown here of representative elements from group 1 through group 17. So what is electronegativity? Well, electronegativity is an atom's ability to attract shared electrons in a bond. It increases from left to right going across the periodic table. It increases from bottom to the top of the periodic table. It is high for the nonmetals, with fluorine as the highest, most electronegative atom, and it is low for metals. And this is a core chemistry skill, being able to utilize these electronegativity values. And you'll be provided the electronegativity values for any in-person assessment, so no need to memorize them. Just want to learn how to utilize them to determine polarity. So once again, fluorine is the most electronegative atom. As you see here, it's 4.0, and there's no units for electronegativity. And it's really high, these values for nonmetals, but for metals, it's really low. So that's a pattern to recognize there. I just remind students fluorine being the highest electronegative element there. And so therefore going across, electronegativity increases, and going up, it also increases, but going down, it decreases. All right, so we're going to use these values to help us determine polarity of the bonds. So if we have a bond between two atoms that have differing electronegativity values, then that particular bond may be called polar, where there is an unsharing of electrons. Okay, so polarity is when there is an uneven sharing of electrons. But if, for example, you have a molecule with a bond, like hydrogen in this case, where they have the same electronegativity values, then this bond would be nonpolar because there's an equal sharing of electrons in that bond. I always like to think about nonpolar versus polar. This is when my kids are playing nicely with each other and they're sharing their toys. This instance reminds me of when one kid maybe doesn't want to share their toy and is trying to pull it away from the other kid. And so that would be a polar bond, an uneven sharing. All right, so nonpolar covalent bonds occur between nonmetals. It is an equal or almost equal sharing of electrons like we saw in the previous example. And there's a very small like electronegativity difference. And so, for example, if we have nitrogen, the electronegativity value for nitrogen is 3. And for this bond, you would say 3 minus 3 is 0. So because there's 0 electronegativity difference, you can classify that bond as nonpolar covalent. If we look at a chlorine-bromine bond, the electronegativity value for chlorine is 3. Once again, you'll be provided these values here. So you can see chlorine is 3 and bromine is 2.8. And so we have 3 minus 2.8 is 0.2. So that's a very small electronegativity difference. So we can classify that bond as nonpolar covalent. If we have a hydrogen silicon bond, we have 2.1 for, let's see here, let's double check that. 2.1 for hydrogen. Silicon is 1.8. And so that's an electronegativity difference of 0.3. When we do electronegativity differences, we always give an absolute value. So this number is always reported as a positive value. So absolute value. So for example, if you had done 2.8 minus 3, then you would have gotten negative 0.2, but report it as absolute value of 0.2. All right, let's look at polar covalent bonds. Now this also occurs between nonmetals, but this is when they don't share nicely. One is more electronegative than the other. And it's about a moderate electronegativity difference. So if we look at, for example, an oxygen chlorine, then that's 3.5 minus 3, because oxygen's 3.5, chlorine's 3. That's an electronegativity difference of 0.5. And so that would be considered a polar covalent bond. If we have chlorine and carbon, once again, this is 3.0 for chlorine, 2.5 for carbon. That's an electronegativity difference of 0.5. So we would classify this bond as polar covalent. We have oxygen and sulfur. Oxygen has an electronegativity value of 3.5. Sulfur is 2.5, and the difference is 1.0. So that's pretty significant there. That is classified as a polar covalent bond. A polar covalent bond becomes more polar as the difference of electronegativity increases. So for example, this oxygen sulfur bond is more polar than this oxygen chlorine bond, just due to the larger electronegativity difference for the oxygen sulfur bond in comparison. The separation of charges in a polar bond is called a dipole. And that is something we can actually measure experimentally, determine the polarity of a molecule. We can measure the dipole moment. The positive and negative ends of the dipole are located. And then what we do is use the lowercase Greek symbol delta with a positive or negative charge. And then the arrow points from the positive. Notice how the arrows, this is called a dipole arrow. Notice how the tail of the arrow is positive, kind of lines up with this Greek symbol delta, this what we call partial positive. It lines up with that. And the arrow is always pointing towards the negative end of the dipole. So this is the positive end of the dipole, this is the negative end of the dipole. And the way we determine what is partial positive and partial negative in a polar covalent bond is just looking at the electronegativity values. So carbon's electronegativity value is 2.5 and oxygen is 3.5. So this one is 2.5, this is 3.5. That's an electronegativity difference of 1. That indeed is a polar covalent bond. Because this is more electronegative, we assign it partial negative. And what that implies is that the electrons in the bond are actually closer to the oxygen. So this is more electron rich, leaving carbon with less electron density, and that's partial positive. So this is like my kid who's not playing nicely and trying to take the toy away from the other kid. He's left without the toy, right? So this is partial positive. And if I asked you to draw a dipole arrow, you put the tail of the arrow, the positive tail, to the less electronegative atom, and then the head of the arrow here pointing towards the more electronegative atom. Now, ionic bonds have a very large electronegativity difference, even more than a polar covalent bond. And we've learned that ionic compounds are usually between a metal and nonmetal. and it's a result of electron transfer. They're not sharing electrons, they are transferring electrons from the metal to the nonmetal. And it has a large electronegativity difference of 1.8 or more. So for example, this is chlorine and potassium. Chlorine's electronegativity value is 3, potassium is 0.8. That gives us a large electronegativity difference of 2.2. And so we could classify that as ionic. You can see here nitrogen and sodium, 3 minus 0.9, 2.1. That's ionic. Sulfur and cesium, 2.5 minus 0.7 is 1.8. That's an ionic bond right there. Now, the difference in electronegativity values for two atoms can help us predict the type of chemical bond, as you just saw. If the electronegativity difference is between 0 and 0.4, the bond is classified as nonpolar covalent. If the electronegativity difference is between 0.5 and 1.8, the bond is classified as polar covalent. And if it's greater than 1.8, then the bond is ionic and the electrons are considered transferred. Whereas in the other two cases, the electrons are shared. Here's a nice table illustrating the electronegativity differences and the types of bonds. And so, for example, here, starting with nonpolar covalent, remember this is the scenario where my kids are sharing their toys nicely. Everything seems pretty symmetrical here. And the electronegativity difference is anywhere between 0 and 0.4. And so that would be classified as a nonpolar covalent bond. Now, if we start to enter the territory about 0.5 to 1.8 or 1.7, then that's a moderate electronegativity difference. And that's when one atom is not sharing very nicely, is a more electronegative than the other atom. And we start to see partial negative. And so, by the way, this is actually illustrating an electron cloud, because we learned in a previous video that electrons take up the space, the volume, right? And so if there's more electron density on one side, then it's going to be an asymmetrical kind of electron cloud. And so if this atom is more electronegative, it has more electrons towards itself and leaving the other atom smaller, right, with less electron density. So this is illustrating a polar covalent bond where electrons are shared unequally. And if we drew a dipole arrow, it would point towards that more electronegative atom. Ionic compounds, electrons are not shared, but rather transferred. And so that's why you see distinct spheres here. So this cation here is not sharing electrons. There's no blending here. It's distinct. It's a cation. It lost electrons and transferred them to the anions. So anions are always larger, generally speaking, than their cations because they have the more electrons relative to that cation. So this is based on electronegativity difference. Anything that's 1.8 or greater is considered to be an ionic bond. Here's some examples of different types of bonds, and then determining the type of electron sharing or type of bond based on the electronegativity difference. So we already saw hydrogen. That's nonpolar covalent. There's 0 electronegativity difference. If we look at, for example, hydrogen or hydrobromic acid or hydrogen bromide here, the electrons are shared unequally. The 2.8 is for the bromine, and then the hydrogen's 2.1. So the electronegativity difference is 0.7. So that's considered polar covalent because it's greater than 0.4, but less than 1.8. And then if we look at, for example, sodium chloride, we see an electronegativity difference of 2.1, which is greater than 1.8. So we classify that as ionic. All right, pause the video. Use the electronegativity values to determine the type of bonds, nonpolar covalent, polar covalent, or ionic for the following bonds. And then check your work with me when you're done. All right, so first we'll need to look up potassium and nitrogen. So let's look at the electronegativity values. So potassium is 0.8 and nitrogen is 3.0. So the difference in electronegativities, anytime you see this triangle here, that means difference, the change in electronegativity. I'm going to take the higher value minus the lower value. So I get a positive value. So that's a 2.2 difference. Did you classify this bond as nonpolar, polar, ionic? Good, it's ionic because it's greater than 1.8. And you also see that it's a metal and nonmetal. All right, nitrogen, oxygen. So let's go ahead and look at those electronegativity values. Nitrogen is 3, and then oxygen is 3.5. So the electronegativity difference is equal to 3.5 minus 3, and that is 0.5. And so that is greater than 0.4. We always say like about 0.5 to 1.7 is considered polar covalent. Chlorine, chlorine. If we look at the electronegativity values here, chlorine is 3.0. But it doesn't really matter here because they're the same. So 3.0, 3.0, the electronegativity value is equal to 0. So that is considered nonpolar covalent. And then hydrogen and chlorine. Hydrogen is 2.1 and chlorine is 3.0. So the difference in electronegativity is equal to 3 minus 2.1, which is 0.9. And because that is greater than 0.4 or 0.5 and less than 1.7, this is a polar covalent bond. All right, thank you for watching. And as always, email me with any questions.